Yeah, so I'm back. So you don't, as I said, you don't have any freedom about in triple point. So in triple point, you have, let's say, F is 0, number of phases is 3, solid, liquid, vapor, and then there is only one component, water. So put into this and you will get P plus F equals to C plus 2. And now if you change any order, you will not, the equation will not get satisfied. So I think that's a good way of remembering the Gibbs phase rule. Now, there is one small term called partition coefficient or diffusion coefficient. Not very important, but just keep it in mind that it is used in liquid liquid separation, and concentration of some component B in organic phase by concentration of B in aqueous phase. Just keep this in mind, small thing. Now there's one. Now let's talk about liquid liquid separations itself. So there's one nice point which I want you to remember nicely is, let's say, this is the general thing. You have A plus B. There's a mixture. There's a mixture A plus B, and then you give C, and you have some C A plus B, and some of the B goes into C, and you get C plus B and A plus some B. So most of the B is here, and you have A. So you had put the C is the solvent. You had put C to extract B out of the AB solution. So this upper part C plus B, which is rich in some C will go down also and some A will also go up, but that is not a big deal. So the one which is rich in the solvent, the component rich in solvent is called extract because it extracted B from the solution. And the remaining one which is rich in the other components, the original components, is called raffinate. Okay, so there is extract and raffinate. So in general, you put an organic solvent to take out organic things from water, but that is not always the case. You sometimes put water to take out ethanol from benzene. So there are things. So just don't remember any one thing. Remember the general definition that the solvent picks out or extracts a component from the solution. That's why the one which goes with the solvent is called extract, and whatever is remaining is called raffinate. Now, this brings us to a very interesting and most probably my favorite concept called triangular diagrams. Why is it favorite? Because one thing that it simplifies calculation a lot, and second thing, it's a bit confusing concept, so you have a very good chance to score if you understand it well. Yeah. So in triangular diagrams, you can have a right angular diagram, right angle triangular diagram, or you can have equilateral triangular diagram. So over here, I am having a image of an equilateral triangle diagram. Yeah. So here I am having an image of an equilateral triangle diagram. Let's say there's some other solvent. Let's say MIBK. So first thing is, how do you read a triangular diagram? So let's first get finished with a right angle triangle because it's very easy to read. So you have A, you have B, and you have C, and there are numbers like 0, 1, 0.1, and so on up to 1, 0.1, so on up to 1, and there are some numbers over here. So basically, whenever you go to a point, let's say this, and then since you take a projection over here and you say that A by A plus B So you assume that C is not there when you take a projection over here. You assume that C is not there, and then you find out, or rather, I have a better way for doing this. You can do this. You can take a projection over here, you can take a projection over here, find what is the concentration here, what is the concentration here. This gives me the mole fraction of B, this gives me the mole fraction of A, this gives me B. And for C, you do 1 minus XA minus XB. As simple as that. That's it. Okay, so you get B here, you get A here. So if a point is here, which means it is pure B, so you'll get B equals to 1, you'll get X equals to 0, X equals to 0. Things like that. So yeah, that's one thing. And then let's go to a triangular diagram. So in triangular diagrams, how do you measure is, let's say I want to measure the concentration of water at some this concentration. Okay, so I draw a line. I draw a line. Okay, I draw a line, and then I measure the perpendicular distance from here. Let's say the distance comes out to be x, or let's use something else. Let's say the distance comes out to be alpha. Then the mole fraction of water, this component, is equal to alpha by height of the triangle. So yeah, basically if this line goes and shifts near water, it is increasing the concentration of water. Now that's how you read it. So basically you can do the same thing for MIB and benzene. That's how you read it. Now let's see what else is there in this graph. What is this shaded region representing, and what are these lines, dotted lines, doing? So the unshaded, let me shade the region nicely. So this represents shaded region represents liquid vapor separation and equilibrium, whereas the non-shaded region represents homogeneous medium. Okay, which means that if you have the system A, comma B, comma C, it will get separated into liquid, and it will get separated into two phases, green. It will get separated into two phases, green and blue, only when the concentrations are in the shaded region. Otherwise it is a homogeneous mixture. Okay, that is one thing about it. Now what these dotted lines are doing, let's say the composition is such that it lies on this point. Okay, then these lines are called tie lines. These lines are called tie lines, and the endpoints of the tie lines represent the composition of the two phases. I repeat, the endpoints of tie line represents the composition of two phases. So let's say the point was here, and you got the tie line ends to be this and this. So one of the phase, let's say one of the phase has the composition this, and the another phase has composition this, and which one is which depends on what concentration is more. So let's say that let's say the benzene concentration is less. If the benzene was, let's say, the solvent, so on this side the benzene concentration is very less, which means that this is the raffinate. So yeah, saying that it is the raffinate gives you the concentration for the raffinate, and then this will be the extract. Yeah, so that's all about triangular diagrams, and that's all for this video as well. Let's meet in the next video.